right, I'm going to go through the exam 1 keys so that you understand how I solve these problems. So in the first one, we have vanadium 2 that tells us it's V2+, and that's going to be our cation. Remember, everything in the cation column has to have a positive charge associated with it. Everything in the anion column has to have a negative charge with it, and everything in the formula column should be neutral. And because everything here is ionic, we know that we're not going to have any prefixes, but we are going to have charges listed if we have a polyatomic ion. So sulfate is SO4, 2-, and because each of these is 2, so we have 2+ and 2-, the formula just works itself out to VSO4. Next, we have aluminum oxide. So aluminum is Al, and that has a +3 charge, so we'll put that in the cation column. And oxide is oxygen with a 2- charge. And this is where we use the swapping method so that we know what the formula of the molecule is. So we will get Al2O3, because that way it will be neutral and add up to 0. In the next one, we have Cr6, so we know that this is chromium, and chromium's a transition metal, so we're going to write 6 as the charge, and then we do our swap to make it neutral. So Cr needs just 1, because bromine is -1, and then Br gets a subscript of 6, because that makes it neutral. Next, we have iron 3 carbonate. Iron 3 means that it's Fe3+. So we'll go ahead and write that in the cation column. Carbonate is a polyatomic with the formula CO3, 2-. So that goes in the anion column. Then we swap them. So Fe gets 2, and carbonate, we need 3 of those because the entire unit has a 2- charge, and so we need 3 of them in order to make the formula overall neutral. Next, we have perchlorate. Perchlorate is a -1 ion, so we'll write ClO4- or -1. Since there are 5 of them, that means that the manganese has to be +5 in order for it to be neutral. So then the formula, or the name, is manganese 5 perchlorate. Then we have KNO3. Potassium is always +1, so we don't have to say the charge. And then NO3 is the nitrate polyatomic. Then we went to the bottom half, and the bottom half was a mix of covalent and ionic. We know that silicon is a nonmetal, so we're going to use our prefixes. So silicon, and then there are 4 of the hydrogen atoms, so it's tetra, and then hydrogen gets the "ide" ending. Next, we have diphosphorus, so P2, and then oxide is O, and pent means 5, like a pentagon. Next, we have sulfur, and there are 6 of the fluorine atoms, so it's hexafluoride. And then after that, we have H in front, so that's how we know it's an acid. We have the nitrite ion with it, so it becomes nitrous acid. We only use hydro as a prefix if there's only 2 elements. We never use the hydro prefix if there's a polyatomic. Next, we have the hydro prefix, so that tells us that it's just H and 1 other atom. That other atom is chlorine, so we have HCl. Again, that's what acid tells us, is that we have H in front. Here again, we have H in front. So we're going to name the polyatomic, which is carbonate, and we know it's an acid. Since this is carbonate, we're going to change the ending to ic, and we get carbonic acid. After that, we have cobalt-2 nitrate, so it's cobalt-2+. Nitrate is NO3-. So before we even get to the hydrate, we have to write CONO3 2. Trihydrate means we have 3 waters. Remember, hydrate or dihydrate, that's from the water. Then, again, an H in front. That tells us we have an acid, and this ion right here is acetate, so we got acetic acid. And I reminded you when we were practicing naming that I would never ask you to name more than more than 2 atoms. So in an acid like this, we have to name all of these atoms as the polyatomic rather than individually. Last, we have carbon tetrafluoride, tetra meaning 4, and again, fluoride comes from fluorine, which is F. People always accidentally put Fl, which is fluorovium. On the next page, we have some of the shorter answer problems that we had practiced. And in the first one, you had to get the formula of aluminum sulfate. So aluminum is a +3 ion, sulfate is SO4 2-, so the formula is Al2SO4 3. That was worth 1 point. So you still could have gotten the rest of the points even if you had the formula incorrect. So once you write the formula, you know how many of each atom we have, so we can find the molar mass of the entire thing. So to get the molar mass of the entire thing, we're going to do 2 times the molar mass of aluminum plus 3 times the molar mass of sulfur, because that distributes, and then 12 times the molar mass of oxygen, for a total of 342.26 grams per mole. And then it was the percent by mass of sulfur, so this is where we do the number of atoms of sulfur times its molar mass divided by the total times 100%. And because the molar mass of sulfur only has 3 sig figs, our answer will also have 3 sig figs. In the next one, this was a sig fig question, very similar to what we did at the start of the semester. So our first step is addition, 249.362 plus 41. In the first number, we have 3 decimal places. In the second number, we have 0 decimal places. So we get 290.362, but we can only report 0 decimals. So this number has 3 sig figs because the decimal comes after the 0. So now if you take a number with 3 sig figs and divide it by a number with 5 sig figs, your answer should have 3 sig figs, and that answer was 4.57. So this one was worth 2 points for getting the sig figs right because it was a sig fig question. Everywhere else, sig figs, I either didn't count them or they only counted for half a point. The next question, people got most of the way right, but the thing here is that most of you calculated molecules rather than atoms. So we have vitamin C, and we have 51.1 milligrams of the vitamin C, C6H8O6. And most of you correctly said that you had to do grams or milligrams to grams. And then the next step was to get moles. So 1 mole of C6H8O6 has a mass of 176.1 grams. So when we do this, this gives us 2.90 times 10 to the negative 4th moles of C6H8O6, which is a molecule. So when we use Avogadro's number, this gives us Avogadro's number of molecules of C6H8O6 for every mole of the entire thing. Because we use the molar mass of the entire molecule, Avogadro's number gives us the number of molecules. So if you stopped here at 1.75 times 10 to the 20, this isn't the number of atoms yet, it's the molecules of C6H8O6. And then to get atoms, we have to add 6 plus 8 plus 6. So we get 20 atoms for every 1 molecule of C6H8O6. And our answer is 3.49 times 10 to the 21 atoms. And the last one This is where we take our abundance and we divide it by 100%, and that gives us the fraction 0.4572, 0.3535, 0.1893, and we multiply it by the atomic mass for each one, for each isotope, very similar to how we did in our practice problems and how we did on one of our quizzes. So when you work out these values and you think about the decimal places related to the sig figs, you'll see that each of them gives you 2 decimal places. So when you do your addition, you get 155.78 AMU with 2 decimal places. Then in the last page, you had your larger empirical formula problem as well as your unit conversion problem. So remember, with this one for empirical formula, we just pretend that we have 100 grams of substance, so we convert all of our grams or all of our percentages to grams, just changing that percent to grams. Then we use the molar mass of each one from the periodic table to get the moles of each one. But this is not where we finish. We can't round it at this step yet. We have to first write that pseudo formula. So once we get this value, these values, we remember that we're not planning to round them. So I'm going to round them here, but in your calculator, you shouldn't. So I have all of these moles for each of my grams, and then I write my pseudo formula. C 5.077, H 11.85, O 1.6925, and I divide all of them by the smallest number, which happens to be from O, so that subscript should be 1. And when I divide, I get C3, H7, O1, and you can include the 1 or not include it. So that is our empirical formula. Next, it says we are given the molecular mass, and we want the molecular formula. So first, we need the molar mass of our empirical formula, which is taken by doing 3 times the molar mass of carbon, 7 times the molar mass of hydrogen, and 1 times the molar mass of oxygen, and we get 59.086 grams per mole for our empirical mass. Then you take the molecular mass divided by the empirical mass, and you get a whole number. And the whole number that we get is 3, which means that once we have our empirical formula, we're going to multiply everything by 3. So we get C9H21O3. So the molecular formula was worth 2 points. The empirical formula was worth 5. The last one required you to know a couple different things, so I can kind of go through what each was worth. So we know that we have a sphere. So when I tell you that you have a sphere, we're probably going to have to use the formula V sphere is 4/3 pi r cubed. A couple people had squared by accident, and since we need r, which is the radius, we're going to start by taking the diameter over 2 to get our radius. So we have to do this step first. Some of you found the volume and then divided by 2, but you can't do that because that already has been cubed, so it doesn't take into account the cubing that happens, and so that was an error. Also, we're given the density in grams per liter. Since we're given the density in grams per liter, we know that usually we have grams per centimeter cubed. And that's the same as 1 mil, and that'll take us to liters. And so that's a good reminder that we should probably convert our feet to centimeters cubed. So I do that right away. If you did that after finding the volume, that is also fine, but you have to make sure to cube your conversion factors, and not everybody was able to do that. So that's just a good reminder to pay attention to your units and label them. So I got the radius in centimeters, and doing that conversion correctly was worth 2 points, either before or after you do your cubing. Next, I'm going to solve for the volume because I know that once I have the volume, since I also have the density, I can find the mass. But because my density is in a weird unit, I'm going to have to convert that next. Okay, so that gets cubed, and now I get 7591253 centimeters cubed. So I'm going to convert that to liters because I know that 1 mil is equal to 1 centimeter cubed, and I know that there's 1,000 milliliters in a liter. So that gave me 7591.253 liters. And notice I'm not really paying attention to sig figs until I'm all the way done with the problem. So now I've got my mass. I know mass is going to be the density times the volume. So I've got my volume, 7591.253 liters, and I'm going to multiply by the density, 0.166 grams per 1 liter. And I get 1.26 times 10 to the third grams with 3 sig figs because that's how many I had in the problem. I had that from the diameter and from the density. Some of you tried to convert your density to mils, but unfortunately what you ended up doing was treating the liters like it was in the numerator, but it's not. That is not correct. It has to be written as grams over liters, and that way you can correctly do the conversion this way. Okay, so this is correct. There are other ways to do it. This is not the only way, but that's how I solved it just for ease and speed. Mainly the issue that most people had was they converted their volume of a sphere immediately and got feet cubed and tried to multiply that by the density right away. Those units are not compatible. So if you did that right away, that was worth 3 points, but you could still earn 4 out of the 7. And there were a variety of other errors, so if anything doesn't make sense, feel free to ask. And that's exam 1.